Thanks very much for everyone coming today, especially because the notice for this talk was only given on Tuesday, I think. So this is really rapid generation of the crowd here.
Infection of news.
Yeah, this is good. This is very promising, actually. So there are some infectious disease modelers here in this room, which I wasn't expecting was going to happen. There is some pedagogical material in here, so just to prepare your mind for some of the results and the graphs that are going to come a bit later on. So I apologize a little bit to those guys, but you know, non-linear dynamical systems, I think you spend a whole lifetime trying to understand them, and they're really never particular, they're never trivial. You always have to spend a moment rethinking how nonlinear terms in differential equations work. I know many others of you from here are in operations research, and then there are others yet who are probably in other fields, which maybe if I finish a few minutes early, it would be great to hear what each one of you, which groups are represented here. But what I'll do is I'll just launch into this, and I generally like interruption and discussion during the talk rather than sort of me speaking from on high and then asking questions at the end, but hopefully we can do both. Don't know what the tradition is here. It looks like you guys don't really have a tradition. Bring massive pots of curry. It's like
help us build the tradition.
It's all pretty ad hoc, so I like that. And I think it increases understanding if we have back and forth dialogue during this, because many of you are from other fields, and it's always a bit difficult to try to understand another person's algebra and whatever else systems they use. Okay, so I'm going to be talking about modelling on front lines. This is a bit of a dramatic title at CDC, and really that's different, a little bit different from academic modelling, although actually this group here does a lot of government related work as well, so I think it's going to be rather similar. The outline, quick outline, very briefly, I'm going to talk about what is transmission dynamics modelling. That's the kind of modelling that I generally do with most of my time, although there are small portions of my time that are taken up in trying to do other sorts of modelling, a little bit more like what the logistics people here do too. What's the purpose? A little bit of a sort of slightly philosophical backstep to talk about what the actual purpose of this modelling is. And then talk about this modelling unit that has recently been set up at CDC, and recently means about 2 years ago when I arrived there, and it was very much more of an ad hoc sort of assemblage of people from various universities before that, and it came about because of the 2009 H1N1 pandemic, and I'll talk a little bit about that and what we're doing now at CDC and how we do it and how it's working out. What is transmission modelling? What do I mean by that? I mean that it's modelling where the contact process, so I'm talking about infectious disease transmission modelling, and the contact process between individual hosts is important. So we're interested in passing on the pathogen from one individual to another, so it's inherently a sort of causal model where we think we know exactly what the cause is of the disease that eventually manifests itself in these hosts. Okay, so the contact process is important. These models might be, statistical. You could just use kind of souped up or turbocharged regression models in which the right-hand side, the explanatory variables, might be the number of infected individuals in a neighbouring county or in a neighbouring street. And you could, your left-hand side, the variable that you're interested in, is the number of infected individuals or diseased individuals at the next time step, okay? So it could be some sort of time series regression model. But because these types of systems are inherently dynamical with respect to time, of course differential equations are a really suitable mathematical device to use. And so the tradition that I come from, which is at Imperial College, and prior to that Oxford University, which is where our group came from, we use differential equations, and I'll talk about that a little bit as well, why we do that. But now, because of course computational resources are not really an object, and we have massively parallel computers, supercomputers, whatnot, we can do individual agent-based models where each individual host and road and truck and airport is modelled individually, so that we typically have over 7 billion agent models now of the entire planet of hosts. And that really isn't so much of a problem. Still takes a few hours to run, typically, and it's a very difficult thing to run multiple times and to fit it to data, but we can do this. You know, this is really becoming quite routine. And then also, particularly just that for CDC, we run health economic analyses on top of these models, okay? Because places like CDC are really always interested in the bottom line, okay? So we're definitely interested in reproduction numbers and things like, is this SARS-like virus going to spread if we only have 15 cases worldwide right now? So that sort of medical issues are really important, but also the cost issues are paramount at a place like CDC. So I'm going to concentrate beginning here on differential equations and that approach. And the canonical model that we use, really sort of the first thing to orient your intuition, is this thing called the SIR, the Susceptible Infected Recovered Epidemic Model, where we look at the host population and we partition it into, in the most simple case, into 3 compartments, those compartments being, and they relate to the infection state of the individuals in those compartments. So very similar to sort of biological or even economic models, where you partition your population into these states and you transition between these states depending upon certain kind of forces that push you from one state to the other. And what we're interested in is susceptible, where you are uninfected, to infected and perhaps infectious, and then recovered or died or in some way removed from the population that is actively participating in the epidemic. Okay, so we partition them like that, and they flow from one compartment or class or partition to the next one, and these rates at which they flow are really important. And the rate we typically refer to as this thing here, we call the force of infection, and we often give it the Greek letter lambda for historical reasons that I'm not sure about.
It was an Australian.
Really?
It was Bob May.
Was it Bob May?
Yeah.
And why did he do it?
Don't know, ask him.
He's a professor at Imperial, actually.
It's the birth
Yeah.
rate.
Oxford.
It's the
No,
birth rate.
Imperial.
It's the
He's
birth
a physicist at
rate.
Imperial, yeah.
Yeah. It's the epidemic birth rate, yeah, because we refer to these as births, because this is, yeah, I suppose because he was a theoretical
It
ecologist.
came from theoretical, well, and nuclear
Nuclear
physics.
physics.
Well, nuclear physics before that.
Yeah. Right.
But then when we have births and deaths from demographic, we have to use a different symbol. Anyway, sorry.
Yeah, no, that's right. And you can see that this is a function of time, okay, in an infectious disease model. Now, that's really critical. If I were teaching a class in a short course or a master's course in this kind of math modelling, I would say at this point, and I'm going to say it now too, that this is really the one sort of take-home fact that one should take home from this kind of introductory talk, because that force of infection is time-dependent, whereas for a non-communicable disease like cancer or diabetes, it could be time-dependent, but it's time-dependent in a fundamentally different way to the way that these ones are. And that way is that basically, as individuals mix with one another, and in this, come on in, as individuals mix with one another, and you see that the turquoise balls here represent the susceptible individuals in that partitioning, and the red ones represent the infected individuals, and you see that 2 of those are coming into contact with each other there, and the red ones kind of passing on its infection in that cartoon way. That as they come into contact with one another, and more of those balls become red, as the number of infecteds increase, the number of contacts between turquoise and red balls, it will increase, and the rate will increase, or at least the rate will change over time. So there'll be this sort of endogeneity of the system, whereby the rate changes because of the flow itself, because of the numbers in the new compartments, and then that will feed back on itself. Okay, so that's the non-linearity in these non-linear differential equations that represent these kinds of systems. And that sort of, in the simplest possible model, is referred to as the mass action principle, which is really the same principle as we see in sort of chemical reaction equations from chemistry and now systems biological equations, where we're also dealing with things like regulatory processes in cells and genetic regulatory processes too. So when you're just interested in those collisions of particles with each other in a sort of perfect mixing assumption, that's referred to as a mass action assumption. Okay, so the force of infection, this thing lambda, is going to be dependent upon the contact rate per unit time, which I call here K, and not just the contact rate, because if you and I come into contact with each other, what we're interested in is how probable it is per contact that I will pass on the infection to you, and I just call that P. And so this thing, the force of infection, lambda from before, is just equal to P times K times the number of infecteds divided by the total number of individuals in the population. So the proportion of your contacts that is with infected individuals. That's what that I over N is, okay? So in the simplest case, that is what the force of infection is represented as algebraically. And I just put that ring around the I there to say that that's the origin of the time dependence of this force of infection, because the I itself is time dependent, and so this lambda is time dependent too. Okay, so back to that flow diagram. So we've got the probability transmission of the contact, number of contacts per unit time, but then once you become infected and or infectious, you then eventually recover in whatever way. You may die, you may move, you may sort of confine yourself, sequester yourself at home. In some way you may be removed from the population, and you do that at a particular rate. Here we're interested in the duration of infectiousness, and if that duration of infectiousness is D, then again the simplest case, the simplest model, the rate at which you exit that I compartment and move into the recovered compartment or the removed compartment is just going to be proportional to 1 over D. So if your duration of infectiousness is really huge, you trickle out of that I compartment very, very, very slowly, okay, in this sort of model. All right, so the model equations, the differential equations that really very simply, you can probably already see this even if you've never done this sort of thing before, represent this kind of system. They involve 3 differential equations, 1 for each compartment, and there's just an inflow and an outflow from each of those compartments, okay? And inflow. Now normally I don't even, when I'm giving this as an introductory talk, I don't even put in the algebra, but I will here, and it's just so simple, and there's an accounting so that an outflow from the susceptible is just equal and opposite to an inflow into the infected, and then you've got your recovery, which is that 1 over D, okay? And that, when you run it, when you numerically integrate, or just integrate, in fact, that model, you will end up with this kind of set of curves, time trajectory of each of those variables over time. And you see your blue curve there is just going to be your epidemic curve, okay, or very similar to the epidemic curve anyway, not quite the epidemic curve.
What's the initial state for this?
The initial state. So it's everyone being, not almost everyone being susceptible, introducing 1 infected into the population. Yeah.
Which is the source of a huge amount of controversy when you're trying to understand data, because you don't know how many people are susceptible.
Yeah, right.
Often very complicated. Right. Initial conditions are hard to establish.
Right, right.
That's why I asked.
But
yeah,
pedagogically, you just said everyone's there.
Right, right, right. So, yeah, so this is infectious disease epidemiology circa 1982 or something, where we would just do a very simple thing, drop a few infected into the population, run it forward in time and see what happens. Now we do all sorts of things, as James was saying, such as running these models essentially backwards, doing the inverse problem of running it many times and using some systematic algorithm to fit the output, usually the blue curve here, to the data which we collect, which are the number of individuals infected over time.
If we go back to 1982, we got that blue curve very wrong for the
Yeah.
HIV epidemic.
Yeah, yeah.
Very much underestimated.
Yeah, absolutely. Yeah, that's right. And I have the that was the Bob May and Roy Anderson published their Nature paper on the epiparameters for HIV in, I think it was 1988, after lots of, years, actually 6 years, 7 years from the first case being identified in San Francisco. We did get it wrong. They got it completely wrong. And they got, the parameter that they got most wrong was the probability of transmission per contact, per sexual act. And they estimated it as way too high. Actually, they estimated it at about 0.05, so 1 in 20, or even 1 in 10, and it was just far too high. It was actually turned out to be an order of even a couple of orders of magnitude smaller than that. For multiple reasons, they got that wrong. I actually have a slide of that paper at the end of this talk, if we have a moment to look at it. One of the great things about this sort of system is, and this isn't always the case with complex systems, even though we do try to do this, is that we have this summary parameter, which we call the basic reproduction number, which again is completely analogous to the equivalent summary parameter from demography and from theoretical ecology. So the number of, we were talking about demographic terms earlier, the number of births, or the number of new individuals in the next generation. So what we're interested in here is the number of births of new infecteds in the next generation. And this is a great summary parameter, and it's composed of 3 parameters that we've already talked about: the probability of transmission per contact, the number of contacts per unit time, and the duration of infectiousness. And if you think about it, if any of those go up, the likelihood of an epidemic goes up. Probability of transmission per contact, more probable we're gonna transmit. Number of contacts per unit time, if it's like measles and we're all in this same room, if one of us coughs right now, actually, we're probably all in trouble. And then the duration of infectiousness, obviously you've got longer to transmit. Okay. And so there's this fundamental sort of kind of guiding light in infectious disease math, in which you have, if this reproduction number is greater than 1, so that you're on average giving rise to more individuals who are infected in the next generation, then you'll have an epidemic, otherwise you will not, otherwise it will die off. Just like, if the population, if the reproduction rate in Italy continues to decline, the number of individuals in Italy is actually going to go down to 0 at some point. I haven't projected when, but it will. And so, again, this is a nice little slide just for your amusement. But this was this parameter, like fairly relatively obscure parameter, featured in this popular movie Contagion. And this scene with Kate Winslet where she is in Minnesota, I think, and writes up on the board, on the whiteboard, the reproduction numbers of common pathogens. It's not bad, actually. It's a great scene. I don't know how many people at CDC itself, even though she was an epidemic intelligence officer at CDC, actually understand this parameter. But that's part of my job to try to make. And flu, you see, is 1. And I already said a moment ago that it's if R naught is greater than 1, that's when you get an epidemic. So, and yet we get a flu epidemic in a sense every single year. So how is that possible? Flu's an interesting thing in that it's sort of teetering on the edge of not happening. And the R naught of 1918 Spanish flu, best estimate is about 1.8 or so, but this, of course, the standard deviation on that estimate is huge because we have very little and quite unreliable data. So flu's a funny one. It's sort of relentless, and the pathogen that we're most afraid of, and there are 500 people working in their own division at CDC, but kind of like an investment bank trading floor of people working on flu, and yet it's this thing that's kind of teetering. But it does come inevitably every single year. And then behind her head, smallpox is about 2.5, I think. All right. So the force of infection, back to that formula that we spoke about. In the simplest case, it's that. But really, in a sense, infectious disease epidemiology has been, its history has been ever more kind of intricate elaborations of this formula. So if you have several, of course we have in the population I was talking about initially, we only have kind of a homogeneous population. Everyone's the same age, everyone's the same gender, everyone's the same essentially. We have no heterogeneity. But in reality, of course, you have a lot of diversity. And so your force of infection equation will easily take that into account by just having several terms that feed into the force of infection. And so you would have maybe age groups, 1, 2, 3, however you would want to partition your population, or maybe risk groups, sexual risk groups for something like HIV, different sex workers, different individuals in the population like sex workers, etc., who would have a very high risk of transmission. Or you might do something like have household transmission, where you're interested in kind of a high rate of transmission in the household and maybe a lower rate in the community, so your formula might look something like that. Or, you know, if you just want to do this in matrix form, it would more generally, the most general way of writing this down would just be where your contact rate matrix and your infected vector are just multiplied together like that. Or you might have spatial dependence, in which case, you know, where you're an individual, you're interested in the force of infection on me, and you guys are all at some distance from me, so we might have some sort of spatial kernel, which we use to integrate over kind of out to infinity, sort of, although not really. And this kind of thing you can take into account in the simplest way. Things like travel patterns too. If I'm a business person and every day I travel to work, well then the distance over which I'm interested in kind of becoming infected is the work distance between home and work, for example, but then also I occasionally take very long distance kind of international trips, and so you might have a bimodal spatial kernel in that case. Okay. And then also time is important. So of course we're not just the same level of infectiousness at all times. If you get, I just came through a cold myself, and I was probably shedding the most rhinovirus or whatever it was about 3 days ago, and I'm probably still shedding a tiny bit right now, but not very much. I'm really at the tail end of that. So the infectiousness curve is going to look something like, it's going to have a peak and it's going to have a tail. So we do things like integrate over those sorts of distributions. Okay, so that's the history of infectious disease math epidemiology quite quickly. But you can see that if I incorporated all of those, the time, the spatial kernel, you know, the different risk groups, the age groups, etc., into one model, which, why wouldn't you want to do that? You might definitely want to do that because they're all very important, and we know a lot about those things these days. We've got tons of data on travel, tons of data on viral shedding, tons of data on risk groups and contact patterns, so why not build them all into a model? You end up with, I haven't said anything about stochastic yet, but why wouldn't you also put stochasticity into a model like this? You would. So you could easily end up with a difficult stochastic differential, integral differential equation to solve, at which point, and a lot of people, that's their business, you know, that's what they do as academics, they solve those equations, and there are still good reasons to work with those sorts of equations, but at some point it becomes easier to build an individual-based model, which from a software point of view might be more tricky, but again, like I said, we don't really have any impediments to building that sort of software anymore. Software engineers are very kind of adept at object-oriented programming, so we can do this kind of thing. So actually, and also from the communication point of view, actually communicating this to public health people, it's very, very simple to have essentially a one-to-one mapping of the model to the world, and have, you know, you can actually visualize these things and have individuals walking down the street. my friend Simon Cauchemet mocks these models and says that they have individuals walking the dog in the park, and that's probably excessive. So model building is about missing stuff out as well as putting everything in, of course. In fact, it's not about putting everything in at all. Okay, a little bit of a backstep about the purpose, again, just to orient you on, to some of the graphs that I'm going to show. So I think there are three purposes to this sort of modelling, and just modelling in general, actually. One of them is combine the assumptions. So we make so many assumptions about what's going on. Like it's a place like CDC, people have so many sort of mental models about natural history of infection and travel patterns and whatnot. You combine them and see what happens. It's an incredibly valuable system to be able to do that. Estimation of parameters, hugely important to estimate things like the reproduction number. And then, of course, finally, the thing that everyone thinks modelling is all about, which is prediction and projection, which I think is important, but not everything.
So presumably,
yeah.
Rather than combining assumptions, it's making people make their assumptions explicit.
Yeah, that too. Yeah, absolutely.
Yeah, the end product is the combining, but
right.
you spend 7 years talking to them, making them realise what they think, helping them understand what they think.
Yeah, right. It's our
Challenging them.
Why wouldn't you include scenario model, right? Modeling different scenarios.
Yeah.
Is that something
Yeah.
that is considered more speculative for the CDC to some extent?
No, not at all, actually. It's a great point.
Yeah.
This is my bias. It's really my bias. People in my group in London just shy away from that. In fact, they shy away from the prediction and projection stuff. I guess I would include the scenario modelling and projection thing, word here. We could talk about that later, but I would lump that in. But yeah, absolutely. People in my group don't make predictions, but I'm always asked for them. That's what people want. If there's a swine to human kind of zoonotic event, if there's a viral event happening, which there was last year at agricultural fairs in the United States, there were 300 cases of swine kids, essentially mostly, going to fairs, these big livestock things. I think they happen here quite a bit too, where kids were, bumbling around with piggies and getting infected. And it happened in about 15 or 20 people the year prior, 300 last year, and so people started worrying about an exponential rise. So people want to know what's going to happen this year and next year, so definitely. It's a long answer to a simple question. So this isn't a model of anything, but all it's to say is that I showed you the SIR model earlier, the susceptible, infected, recovered, but it's hardly ever really like that. And the more information that we have, the more complex this sort of model can become. So this is, of course, this isn't to really understand, but it's just to say that this is actually a really simple model, and if you put upon that age and other risk groups, then you've got something which has got a lot of parameters quite quickly. Nothing compared to systems biology models, I hear, which are thousands of parameters at the moment, and but they're actually making headway as far as I can tell, which seems miraculous to me. So then what if that antivirals thing there was just to say, what if your boss, Rear Admiral, whoever at CDC says to you, what happens in this model if I administer antivirals to these guys in this population? This kind of building a model in software can help you to just answer that question rapidly if necessary.
I have a question.
Yes.
Maybe you'll get to this at some point in the talk, but
Yeah.
Is there an understanding of how rich or complex these models need to get so that they can be fit to, say, those simulations of every agent?
So let me understand that question more. Let me say that back to you. No, actually, you say it to me.
Okay. So if I have my agent simulation, and I want to be able to understand it in this kind of a model, how complex is needed? Do I need to have 100 different populations? Maybe this is with just 3 groups. Maybe it characterizes it.
It's great. That's such a great question, and so much. I think it's a art. at the moment, and I don't want it to be an art for too much longer. I mean, it seems silly to me. I think there are probably formal methods whereby we can sort of, I don't know, James, what you think, or others, but I think there are formal methods that are on the way, and we really should concentrate on developing them. Because there's, Bob May is such a proponent of analytical, mathematical work and insight through, solving equations on the back of an envelope or on a piece of paper first, and then running your computer simulations. I agree, I don't think you should jump to those. And so the more model reduction you can do, the better, the more analytical insight you can get. So it's an art at the moment, unfortunately.
My answer to that would be surprisingly few compartments. Like the simplest model fits so much data you'd be terrified. It's like bizarre how good it is. And the only other thing I'd say, Alex Schwarzkopf from DSTO here has actually done some quite nice work on that precise question. He, using an SI model, he was building simulation models, doing stuff, making slight changes away from SIR, and then quantitatively, like figuring out what the biases and errors on the parameters were if you then refit just the straight epidemic model. Right. So he's got some nice work that he published last year on coming out of Fisherman's.
Yeah, anyway. Yeah, no, that's good. I'd like to see that too.
Yeah, I can see.
Yeah, that'd be great. Because there will be biases.
Yeah, so that's what he's trying to pick up, is when you just inflate it, you're not sure, and when you actually get things wrong, you pick up some of that. Yeah. But it's very, very early kind of work, as you're saying. It's a bit of an art. Yeah. There's some case studies around.
It seems kind of analogous to in machine learning when you take a big pile of data and you try to fit a graphical model to it. Yeah. Except here, instead of the machine learning type of things, you have these time-dependent equations.
Yeah. I mean, I think that increasingly, so groups like Microsoft Research, they have the infer.net thing, and then WinBugs as well. There's support for you doing differential equation models. So we're in exactly the same territory as they are now. Not just analogous anymore, we're in exactly that territory. And I think machine learning summer school and all that stuff, there are people who talk about this stuff nowadays. Okay, so you've got that model, then estimation of parameters. So you've got, here's how the system works. You've got your input parameters and initial conditions, just as James was talking about a moment ago. The number of susceptible, the proportion of individuals in the population who are susceptible. Why might that be less than 100%? Just because either you're vaccinated or you've already experienced the infection before, and so you have some existing immunity, for example. So you put those in, and out you get model outputs. And what might those model outputs? Well, those model outputs I'll say in a moment. But your inputs are going to be things like recovery rate from infection, or the duration of immunity, stuff that we kind of mentioned a little bit in passing earlier. And the reason that I've got priors, so those are priors, as you no doubt have intuited, and they've got width to them, and so they're uniform priors with width, and they should have width, because we're never completely certain about what they are. And that's really a major difference between the way that this discipline used to be practiced 20 years ago or so. We can do this kind of computation now. And so because we've got width on our inputs, we're going to have a multitude of outputs. Okay, so that's something like the prevalence of infection. I haven't put anything on that axis, perhaps I should have, but it's something like the prevalence of infection or disease with age. And each one of those curves represents a kind of realization of the model with a different kind of pick from the distribution of prior inputs, okay? But we don't stop there, because we can go out and collect data, and that's what these wiggly lines and crosses mean. So that's sort of the 95% confidence interval of those crosses. So we might be able to just go out and do serological tests on people to figure out how many have become infected over time. And we can then eliminate those outputs, essentially. I mean, there's a little bit more complicated than that, maybe, but not much. Those outputs that don't fit those data. Okay? And then with that knowledge, we then go back to the inputs and we can narrow them down. And there's still not Dirac delta functions, but they still have width to them. but it's significantly narrowed down, and also it's kind of shifted one way or the other. And it might not be uniform, but I've drawn them uniform. And so I'll put a ring around that, because that is really it's one of the major areas of research at the moment in this discipline, and in systems biology, and in econometrics as well. How do you do that? How do you take uncertain input parameters, generate outputs, kind of eliminate those which don't fit the data, and then feed those back in again? And how do you do that in a computationally efficient way? And that is really so much research is going into that at the moment. A large proportion of people like Imperial are doing that. Yeah.
And the assumption there is the model is correct, right?
Yeah. Yeah. That's very, very good point. Yeah. And so on top of that is this other layer of model selection, testing models. Yeah.
Locally, should we use Australia, New Zealand and Tasmania as 3 separate islands? And therefore there's 3 lots of data for doing this purpose?
Yeah. Yes, I would say so. In general, for this kind of model, yeah, I would say so.
For other diseases, you've got to go down to state by state, because you can get very strong seasonal, like climatic effects. So you get different timing of seasons. So every particular disease, you need to make sure you don't homogenize where you should not have.
In particular, in winter, the people in Melbourne migrate to Queensland, don't they?
Well, there's that, but there's also just literally different seasons, like diseases come at different times.
Yeah, absolutely. Yeah.
So.
Yeah, but yeah, model selection being so important. I mean, such an over-ignored source of uncertainty really could just like negate all of your results if you haven't checked which model is the best model. Okay. And then finally, the projection thing, which is when you've got your narrowed down input parameters, they fit those data that you've collected, and you can sort of take your model for a spin and run it to see what it gives for a output that you hadn't previously run it for, like incidence of disease, for example, where you've still got output uncertainty, but it's perhaps narrower than it would have been previously. Okay. So that's your projection or scenario analysis component. Forgotten why I put that there again. It's there for a reason. So all I wanted to say there was that, again, this is the old school way of doing this. It's a single curve, you run it forward in time. The Anderson and May paper from 1988 on HIV/AIDS the graphs look very much like this, single lines. This is an example of, so that process, of course, is a Bayesian process, or has come to be known as a Bayesian process recently, and that's where the focus of these sorts of algorithms is. This is a paper from 2011 in PNAS from colleagues at the Health Protection Agency, which is sort of the UK's version of the CDC, where they have a really good and considerably better equipped and bigger modelling and economics group than we do at CDC's. And we're actually sort of modelling our group at CDC on what they have built in London. So sort of half modelers, half economists, and we teach each other. So here's what they did here, and the graphs that they got. And the interesting thing I wanted to just show you here is that, so this is the H1N1 curve of the model in London. And what's going to happen, I'm going to show you a sequence of 4 graphs from this paper. What they've got here is they've given their model only as much data as is up to the red dotted line, okay? And then beyond that they project. So you can see it's completely sort of accurate up to the red dotted line, and then it's got wide uncertainty bounds because you haven't given it much to train on, okay? And you can even see that it's like one of the, you've got one mode of kind of peaking here and another one there, and then this is kind of an average, but who knows whether any of the curves in here really do that. Okay, so then the next one, they give themselves data up to here, week 37, 38 or so. The black dotted line here is where they previously gave themselves data to on the previous run. And you see that something very different is happening. The lighter grey shaded region is the previous uncertainty envelope. And you can see this is the new uncertainty envelope. And it's narrower, and it's also double peaked at this point. So they've given themselves more data, and they've got this double peaked kind of projection forward in time from here now. And it's bound to do that at this point, because you've got data telling you it's going to do that. But they've got their model telling them that it's going to come back up again in the autumn of 2009.
So why is there a shaded area between the two dotted lines? Why don't they know that exactly if they have the data?
So they have data. So they have data up to here, but okay. So their model. So I guess it's a stochastic model, and it's saying that even with the parameters that they've estimated between, up to here, it could have the curve could have come out like this. Okay. So it's a sequence of stochastic runs, but it's considerably narrower. And then further, you see that basically the double peak structure is maintained, and then the difference between the last two is really is quite minimal. And this kind of raises the question of how much data you need to feed your model so that it comes up with a decent prediction. Obviously, as little as possible. If you could come up with some sort of idea that you could model as few data points at the beginning of the epidemic as possible, then you could make a decent prediction. The better for people at a place like CDC. But this tells you something about, do you need, that initial upswing of the epidemic gives you kind of a quantum of information. It tells you the exponential growth rate. Then where it starts leveling off, and where it peaks the first time, it gives you a quantum of information. It tells you kind of what the size of the susceptible population is, because it's beginning to saturate at that point. There's another thing going on here, which is schools closing for the summer, which kind of makes this, so that's the seasonality, but also just like this social pattern happening. So perhaps that's another quantum of information in your model. So this idea of sort of mutual information, if you like, between the model and the data that are being collected is another thing that's live, and a few people are thinking about it, perhaps not in using the word mutual information or those sorts of machine learning type terms, but there's certainly some people at the University of Michigan who are thinking about this sort of thing. So I just wanted to illustrate to you an example of that sort of Bayesian modeling that I was talking about.
Did they have any data to validate the model?
Yes, so this was all based on data. Just look.
But the red line isn't what really happened, right? That's the mean of the stochastic. So how does it match up with what really happened?
No, the real line is data.
No?
No, the red line wasn't data. The red line was the best projection. The data actually were not shown in that.
The data looks like the red line, though.
The data looks, by the end of it, the data looks a lot like the red line.
Okay.
Yeah.
Are you very dependent now on the quality of the data, especially in the early part of the epidemic? And so if you do have underreporting, aren't you most likely to get your parameters wrong and underestimate?
You are. And actually that's what this paper was about. It was about underreporting, GP reporting rates suddenly changing at the beginning, and it's an interesting and messy paper. It's just the sort of thing that PNAS should publish, actually, which is, I think, they do publish some good stuff.
The outcome of all of this...
I got the paper published there this week.
Well done.
So I guess you won't like that paper.
The outcome of all of this was there's a huge effort going on, including in Australia, about trying to develop methods to collect the appropriate data in a cost-efficient way, so that next time we've got some hope of actually knowing what might be about to happen. So this has prompted us to realise that the way that we collect data at the moment is completely inadequate for monitoring something like an influenza pandemic. And the government's throwing money at this right now in Australia and in the UK. And there's a huge effort going on. It actually initiated a whole funding stream in the UK to fund groups to have on-the-ground protocols in place, so they're grants for the future, and if the event hasn't occurred in the next 3 years, you give the money back. And you've got to have pre-ethics approval. I mean, there's a regulatory process here about ethics and everything that ties up. So people are thinking very carefully about how to, both scientifically and in politically be able to get the data that we need so that we can do projections and not just
are you looking for data that are up to date within days, weeks, months?
Yeah, absolutely.
Which?
Days to weeks.
Yeah.
Months is months is only helpful for retrospective. The government rings up, they did me in 2009 and said, what's going to happen tomorrow? It's like, I don't know, but I can guess in my crystal ball. So,
and they asked at CDC how many people are going to, after day 5 or something, how many people will be dead by the end of this?
Yeah, I had those questions every day on the phone in 2009.
A simple example is the deaths. On deaths, I know from work I did that there's at least a 3-week, on average, delay between the death and the death actually being reported statistically. If you eventually collect the actual date of death, you can compare the 2 time series and very clearly establish there's on average a 3 weeks delay just on the simple matter of reporting deaths.
Yeah, right.
And the other thing there is you also die after you're infected. So if any point in time you take the number of deaths and the number of infections, that's you've got that. So for a case fatality rate sort of thing, you've got that wrong as well. And so generating protocols to collect information appropriately powered, statistically powered, so that you can try is a big effort, and it relies on models to generate synthetic stuff to think about.
Yeah. Anything that's, in general, I think anything that is a systematic bias, so that if you really can kind of put in concrete that 3-week delay, if it's systematic, we can deal with it. If it's unsystematic and nutty and crazy and random, even if it's random, if it's truly white noise, then we can probably deal with it. But if it's kind of randomly random, then we're in trouble. Okay, so because of the 2009 pandemic and the kind of visiting, let me just say this, because of the 2009 pandemic, CDC needed to be able to do certain things like calculate parameters like R0, but also, more importantly for them, things like projections of incidence, just as we were talking about, and projections of the final mortality and that sort of thing. But also, because there are an increasing number of groups like working on this stuff, smart academic groups who can publish, who can get manuscripts ready so damn fast, and so we have to read this and react to this. CDC doesn't have that part of its kind of organizational brain to do that, so we needed to be able to do that.
There were huge numbers of data analysis, modelling-based data analysis papers out within 2 months, 1 month. Bureau Surveillance had a 5-day review and published within 5 days, like turn around.
What do you mean by data analysis?
Trying to understand, so data was coming in through wherever, ministers making announcements and Mexico publishing what happened there, and people were analysing the data, trying to understand what it might imply, calculating reproduction numbers, and they would be published online within 10 days to 15 days, having gone through review. But it was because they knew if that didn't happen, it was being published as a way of disseminating it because people needed to know the value of the numbers. So those numbers also would have been read over the phone to relevant governments. It was a way of trying to find the balance between getting your academic CV built appropriately and providing a public service. It's a real tension in this field.
Sort of projects that we have throughout CDC are Pertussis. So Pertussis is resurging, I think in Australia possibly more than anywhere else in the world at the moment, as James and others in this room know about intimately. And in the United States too, so probably second in the world in terms of, other than New Zealand perhaps, is the United States. So rise in the overall number of cases. This is a vaccine preventable disease, but it doesn't seem to be happening mostly because of vaccine refusal, which is the obvious kind of candidate reason. So what's the dynamical reason that that's happening? Mumps, also a little bit of resurging going on. That's possibly more to do with vaccine refusal though, because of the MMR vaccine and this whole kind of movement to refuse that vaccine because people think it might cause autism. And then influenza, kind of perennial question for the last few years is, what if we don't have a vaccine or antivirals or pharmaceutical interventions, what happens if we do things like close schools? What sort of effect will that have? So just to give you some graphs and background on pertussis for a couple of minutes. This is in New York Times from 2010, big epidemic in California, but then in 2000, people thought it was gone. In 2010, it was the worst in 47 years, but then 2012 was even worse. So almost back to the times when there was no vaccine, it was almost as bad as that. In the UK, it's happening, and then also here, it's been happening. This is Australia. So it's been happening since, really slowly, since the early 1980s. There was a vaccine that was introduced in the 1940s, which was the organism itself sort of killed and kind of put into a pill. DTP means diphtheria, tetanus, pertussis, so it was part of the triple vaccine. But then, because there were some kind of negative effects of that vaccine, reactogenicity it's called, so disease associated with the vaccine itself, that was changed to an acellular, sort of artificial one, which supposedly had just the important proteins in the vaccine itself. Okay, so sort of immunogenic, so to develop the right immunity with just very few of the components of the bacteria itself. So the question is the effectiveness of this vaccine that was introduced in the 1990s perhaps responsible? Is the effectiveness different anyway? So this is the curve for the United States, and so this is over time and the number of cases on the y-axis. That's where the that's where the vaccine was introduced in about 1947, and that's where the new vaccine, the acellular one, was introduced. This is actually a teenage boost vaccine, so same components, but just an extra boost. And you can see it doesn't look incredibly dramatic here, but it's really quite big, and if you draw a line back all the way, this is where you get a similar sort of disease rate. And there, it was really almost eliminated, okay? So it's almost gone in 1976, but now it's really back, and it's coming back pretty steadily. This is Australia and New Zealand. The green line is the American one I just showed you, and you can see that sort of it's zigzagging all over the place and going up quite high in Australia. I'm not going to say too much about that. The experts are in this room. I should talk to them about this too, actually. And then in the UK, something similar is happening there too. I'll skip over that because we've got very little time. I like infographic type of things, and so Philadelphia Inquirer did a really nice one, I thought. Very simple, very nice for the US epidemic. Okay, so back to that. The inset there is just a kind of zoom in on the most recent times. So 2011 was bad, and then 2012 actually went up even higher. But another thing's going on, and that is that there was a peak. So this is now over age, not time. So this is over age. So this is the age distribution of cases in 2000. And you see that there's that adolescent peak, which kind of disappears by 2009. So in the US, the new peak is kind of shifted that way. Okay, so that's the other pattern to explain in the US. Increase in cases, but also a shift in this pattern. So we built a very simple SIR model, so that's just like what I showed you at the beginning. We added a couple of extra sort of bolts, but we bolted on a couple of extra bells and whistles to it. And what we end up with is kind of our model uncertainty envelope, and the black crosses are the data, and the blue line is the mean of the model. So this is just like what we saw for the influenza paper, except now we've got the data illustrated here as well. You've got this funny thing happening here, which I can't seem to get rid of in any model outcome. So it seems to me that it is possible that it happened, and actually we're looking into this to see whether there are any reports from around this time which are in some way neglecting outbreaks of pertussis that were happening around here. So dynamically, I think it could be possible that we missed due to kind of thinking that it was almost gone perhaps, and attributing pertussis to another disease, which is easy to do. And so what you can do when you end up with fitting a model to the data like that is you can project forward in time. So what we've got now is the same model, but now projected forward in time. and there you have your mean, and your black dots are the data, and the grey shaded bits are the model output sort of envelope of uncertainty. And you can do things like, so this is the great thing about these sorts of models, you can simulate interventions. These aren't just statistical models which kind of explain the data, they actually allow you to do simulations. And so if you were to give a booster vaccine to adolescents here at a kind of, let's just say, maybe don't understand what that quantity is, but just say it's sort of intensity of giving the vaccination to that part of the population. If you do it at a 10% level, 40%, 70%, 90%, you could, that's very infeasible, by the way, that 90%. So even though it looks like it's containable, this upsurge, 90% is probably a completely infeasible level of extra vaccination to give. But this is a nice sort of projective thing that you can do with these sorts of models. And then cross-sectional, what we've got here is, so age along here, incidence here, 1990, 91, 92, 93, 94. So we've got that sort of age distribution changing over time, 95 to 99, 2000 to 2004. This is all data, so real data. And just to orient you, that's that adolescent bump in 2000. And that's the new peak in 2009, which happens at a slightly younger age group. And this is the model sort of envelope. And it's not bad. I mean, in terms of like explaining the features, rising disease on average, the envelope of uncertainty is big, but it does in general show the same phenomenon, including the shift down in the disease from the adolescents down to a slightly younger age. It's missing some, but honestly, that's not half bad. Okay, I think I should be basically done now. But school closure, this is actually not my work, this is Simon Calchemet from London, and all he's showing here is we're back on time again. Different flu seasons are each one of these graphs. The blue bars indicate where schools closed, and all he was trying to do here was say, was there significance in the downslide of the epidemic when schools closed? And he found that there was a significant effect in France. So this is a lovely paper from 2008. But he also did something really nice here, which is he matched the trajectory. So just like, so it's kind of very similar to a Kalman filter methodology, where you, in a way it's really for show, because people always have a lot more trust in a model that really matches the data very well. And so Simon is actually, one of the things he's doing is working on fitting methods to estimate parameters, but also to really match trajectories in stochastic situations, right? So not just kind of the smooth epicurve, but the stochastic epicurve. But what if your data don't look like that, and instead look something like this, right? So global snapshot of disease, or this, which is global snapshot of disease plus air traffic from Mexico, which is what those black dots represent. And your model output looks something like that, which is Alessandro Vespignani's agent-based model of influenza. So what if you've got this kind of big 7 billion agent-based model, and your disease data is, or our kind of global snapshot of disease spatial pattern? Okay, what in the heck do you do to fit this model to those data? This is, well, I don't know is the answer to that question, but maybe we can do, maybe we can take methods from pattern matching in kind of visual pattern recognition to try to use fitting algorithms to fit agent-based models or individual-based models to those sort of data sets. Or we could, one thing we're going to have to do is choose appropriate statistics to summarize those patterns. And that's an area that this area of approximate Bayesian computation is really looking into well at the moment. But then also model reduction, which is what we mentioned earlier. Okay, this is the end, really, nearly. I'm going to summarize what we can do. We can fit increasingly complex models to data. We can quantify uncertainty quite well, including predictions, and we can quantify the impact of interventions. What we hope to be able to do We hope to be able to build bigger, more intuitive models, so that while they're bigger models, they're also more intuitive because they are one-to-one maps between the real world and the model. Do better parameter estimation and inference, like they do in systems biology, but we're kind of co-evolving together. These fields are co-evolving, but also in data assimilation and things like climate science, where they have 100 million equations to solve, and they have 100,000 data points to, to fit into those models. Better uncertainty, measurement, better, oh dear, word missing. Don't know what that word would be. Anyway, better quantification or something like that of uncertainty. I think I was just looking for the perfect word and never found it. But that's a really important one, as you were mentioning a moment ago. Model uncertainty, really important, and something that we neglect too much. And that just means choosing the right model, or at least a suite of models. And then something that's, I think, perhaps as important or even more important than all of this, to integrate these sorts of analyses onto the desktops of public health people, because they can't do this. So we sort of need the mathematical modelling version of an iPhone or an iPod or something, which has a kind of okay, I'm not going to go there. But they should do what they're trained to do. But until they're trained to do this, which they're not trained to do, and they might never be trained to do this, they should be able to somehow still work with these tools, but not have to do the code, write the code, or the algorithms. But maybe they should.
Well, at the moment they work with inappropriate and dangerous tools sometimes.
Right.
Like what?
People's expert opinion and crystal ball gazing completely. I don't know what your experience is.
Oh god, it's horrible.
Yeah, it's in the absence of good practice, you do whatever the best thing you can do, and most of these people might have come from a clinical or a public health background, and they're not trained, they don't think about it as a system. The idea that there is it's a dynamical system, it's transmit, that doesn't even, they don't think about it that way. And they do, then they do what's...
So we have a Masters of Public Health, which must teach them all that.
It's actually, they're good programs, but they don't necessarily teach people, they're just not people who think like everyone in this room does, necessarily. They can be trained to think like this, and over a long period of years of conversation, you actually get to a really good spot. But
yeah.
I mean, why isn't the solution just have them work in collaboration with technical people, such as yourself?
Well, it is now.
That is what's happening.
It is now, but
that's not it.
No. And my friend Stephen, actually, who I gave a plug to, he's in Santa Fe, New Mexico, and he's such a creative person, and he came up with this sim table. I think tabletop exercises are a known thing, but he's taking it to another level. He's kind of what he refers to as ambient computing. Other people refer to it too, so that you can manipulate these surfaces, do the computing on the projection itself. So you don't have an iPad or a device, you actually manipulate on the projection, and it reads off. The projector is kind of alive as well. So this is for disaster management. He's worked with the city of Boston, he's worked with the Secret Service a little bit in the United States, and he works primarily though with wildfires, so people who deal with wildfires, and sort of do predictions essentially. Where might it go if this happens, or the wind changes, or there's more fuel in this part of the mountain than we thought, or this kind of thing. And I want to work with him a bit to try to kind of incorporate some data assimilation or more kind of advanced modelling tools into his kind of what is essentially like projecting data onto three-dimensional surfaces. But he also says though that his kids, as so often happens these days, they have internalized dynamical systems from gaming, really. And so they know about nonlinear dynamics and sort of push-pull effects and disproportional, you do this and you have a tipping point in a game. So they've internalized it without knowing how to do the mathematics. That's something I think we could leverage in people who aren't necessarily trained to do nonlinear dynamical systems math. it has to lie behind all of it, but we could train people to do that perhaps. Anyway, thank you very much for your time.